computer's like being annoying. There we go. Okay, so let me change to, good afternoon, good afternoon. I'm gonna change to writing mode, and we're gonna pick up where we left off last time, which was talking about distributions of variables. So let me sort of remind you of what that was about. So when I'm talking about, oh, whoa, my webcam is like not showing up right. Let me fix that. I'm like cut off. There we go. Okay, so when we talk about distributions of variables, we want to look at one variable at a time, and we sort of want to look at all of that information from that variable. Okay, so when I talk about the distribution of the variable, the goal is to look at all of the values somehow, at all of the values for all the subjects at the same time. And we want to, what we're going to do is we're going to look for like trends and patterns. Stuff like that. We want some sort of global view of what's going on with our data. Let's change my camera a little. There we go. Okay, so that's the goal. And last time we talked about this a little, and I told you that depending upon whether you're talking about a numerical variable or a categorical variable, you're going to end up doing different things. So today, we're going to talk about how do you look at the distribution of a numerical variable. Okay, so there you have these numerical variables. How do you look at them? So I'm going to start just by making up some numbers. Or actually, should we make up numbers? Let's take some numbers from the crowd. How about that? Okay, I want you to put into the chat how many siblings you have. And I'm going to write them down as I see them. 3, 4, 1, 3, 1, 0, 1, 3. I'm assuming 22 is actually 2. 2, 2, 3, 1, 2, 6, 2, 3, 4. I'll put, for me, 6. Actually 5, my bad. Okay, cool. Okay, cool, that's enough. So we have numbers here. So this could be the variable number of siblings. You would like see it in Wolfram, it would be a column. So let's call this variable number of siblings. Okay, and it's definitely numerical. And what are your two options for numerical variables? Do remember there's two different types of numerical variables. Yes. So what makes something discrete and what makes something continuous? Do we remember? That's good. We got the names. So now, how do you know which one it is? Like, what makes it one versus the other? It's something that you count. Yeah, by fixed, usually people mean like their whole numbers. And number of siblings is something that you count, so this is a discrete numerical variable. It's not continuous, because continuous would be measured. They'd possibly have a decimal. Cool. Yeah, discrete counts, continuous measures. So what we have is a discrete numerical variable here. And what we want to do somehow is like look at all of these numbers and figure something out about what's going on with like, you know, how many siblings people have in this class. So usually one of the ways that you start looking at and analyzing these variables is by looking at them with a graph. So a graph is a way to visualize the numbers. Okay. So we're going to talk about like different ways that you can visualize these numbers. Okay, a very common method to use is called a dot plot. And what a dot plot does is, because it's discrete, you can count to see how many of each value there is in your data set. So we would start right here at the value 0. And you ask yourself, well, how many people in this data set did you see who responded with a 0? Hopefully you can see that this 0 right here is the only 0, right? Okay, so there was one person who said they have 0 siblings. So we would put 1 dot right here. That 1 dot represents the one person who had 0 siblings. So 1 dot, because there's one person with 0 siblings in the data. Okay, and then you would move on to the next number. So the next whole number is 1. So then you look to see, well, how many people responded with 1 sibling? I'm assuming that's not 13. So here's a 1, here's a 1, here's a 1. So I see 3 1s in the data set. Actually, no, my bad, 4. 1, 2, 3, 4. So I would put 4 dots here. 1, 2, 3, 4. Okay, and then you keep going through. So I would move on to 2 next. You count how many people responded with a 2. So I see 1, 2, 3, 4 people. So again, I would put 4 dots. And then you move on to the next one. See how many people responded with 3 siblings. 1, 2, 3, 4, 5. So I would put 5 dots. 1, 2, 3, 4, 5. Okay, the next number is going to be 4. Count how many 4s there are. 1, 2. Okay, next number would be 5. I see 1 5. It was right here. Let's mark it off so I don't see it later. Let's also cross off all the 1s. Cross off that 0. And there's 1 number left, the 6. And now we've got everyone. Okay, so what's nice about this is that when you turn your data into a graph, you can start looking at it in a systematic way. So you can use this graph to answer questions such as, which value occurred the most? Which value occurred the most often? And that's an easy question to ask. You can see that this is the one with the most dots, in other words, 3 siblings. 3 siblings is the most common number of siblings in our data set. You can start asking questions like, what was the least number of siblings? You just look all the way to the left. People had at least 0 siblings. You can go all the way over to the right and you can ask, what was the most number of siblings? That was 6. No one had more than 6. So looking at the graph, you can see things like, oh, well, people had between 0 and 6 siblings, and 3 was the most common response. Okay, so is everyone just sort of getting how I can see that from the graph? I just want to make sure we're cool on that. Okay. Good, 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 good. Okay. So, talked about that. Oops. Everyone probably heard my dog. Okay, so you know how you probably heard the term average? like someone has the average number of siblings. So you can start wondering, like, what do we mean when we say that? So let's type this down. So what would it mean to have the average number of siblings? So that's what we're going to discuss. What does it mean to have the average number of siblings, or what is the average? Okay, apparently I spelled siblings wrong. It only has one B. So the average is a special example, or is an example of something called a measure of center. Okay, so every distribution has what we call a center of the distribution. Okay, and the center of the distribution is basically the most common or average, or however you want to say it. It's a single number that somehow describes what's usual for the numbers you have. So you can sort of think of the center as what's a usual or typical value. So whenever you hear the word, like, it's the average, you can think of that as meaning normal, typical, usual. So how do you look at all of these numbers and decide, hey, what's typical? Like, there's a lot of different ways to do that. So you could say that the center or the typical value could be the one in the middle. So the center could be a middle value. It could be the value which occurs the most, or something else even. The fact is that it's negotiable what you mean by typical. We could say that what's typical will be the number in the middle. We could say what's typical is the thing that happens most often. Or you can come up with some other way of describing it. But the fact is that when we're talking about the average, that we're trying to say that that's what's typical about what you're seeing in your data. So a very common measure of center is what is called the mean. Sometimes people call this the average, but there are many different types of averages. The mean is a particular example of one sort of average. So the mean is a measure of center. It's a way to tell you what's typical for a distribution. So the mean is a measure of center. In other words, a number which quantifies what is typical for the data you have. And the mean is probably the average that you learned about in high school or grade school. So if you have a bunch of numbers, how do you compute the average? Do you remember the way to do that? Yeah, awesome. Yeah. So you add up all your numbers and divide by the number of numbers. Okay. So if x1 would be your first number, x2 would be your second number, x3 would be your third number, and so on, all the way up to your last number, which we'll call xn. So in other words, you add up all your numbers and then you divide by how many numbers you have. We always use the letter n to refer to how many numbers you have. So like this is how you would write it in mathematical notation. Each of those x underscore numbers, that refers to like the first number, the second number, the third number, and so on. The nth number is the last number. Then you finally, what do? Divide by the number of numbers. Okay, so whenever we're calculating a mean this way, the way that we know we're talking about a mean is we put a bar over your variable name. So like if your so let's say our variable was called siblings. If you wanted to take the average of siblings, you would write a bar over it. Does that sort of make sense? Like siblings with a bar written over it tells you that that's what the average of that is. Or the mean. I should say the mean, not the average. So are you ready to do an example where we'll calculate the mean for the numbers we had that you guys all gave me about the number of siblings? So I'm going to scroll up and we're going to copy that. So I'm just going to copy this stuff. Hopefully I can copy it. Oh shit. Okay, we'll see. Let's see if it will let me copy it. Oh, sweet, this is cool. I literally just copied it all from there. Imagine if you could do that like on the board in real life. Like, I understand it's probably not a big deal for you, but for me, like, because I have to do this all the time, it's like sort of amazing. Oh, a smartboard? Was it a smartboard? I actually had one of those. I taught at a high school for a couple years, and for like a year or two I had one, and I'll be honest, it was pretty awesome. No one else really used it like I did, but yeah, I remember able to do that. It was pretty awesome. I loved it. Okay, so let's calculate the mean for all of this. So to calculate the mean for all of this, you literally need to add up all these numbers. So you're going to do 3 plus 4 plus 1 plus 3 plus 1 plus 0 plus 1 plus 3 plus 2 plus 2 plus 3 plus 1 plus 2 plus 6 plus 2 plus 3. I sound like I'm singing really horribly. Plus 4 plus 5. And now we need to quickly count all of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There were 18 numbers, so I have to divide by 18. Okay, I'm going to start just doing the math in my head. 3 plus 7, 3 plus 4 is 7, plus 1 is 8, 8 plus 3 is 11, 11 plus 1 is 12, 12 plus 0 is 12, 12 plus 1 is 13, 13 plus 3 is 16, 16 plus 2 is 18, 18 plus 2 is 20, 20 plus 3 is 23, 23 plus 1 is 24, 24 plus 2 is 26, 26 plus 6 is 32, 32 plus 2 is 34, 34 plus 3 is 37, 37 plus 4 is 41, 41 plus 5 is 46. So that number on top ends up being 46. So you get 46 over 18 is the average number of siblings. So I'm going to write siblings with a little line over it. That's how you know you're talking about the average of the mean of siblings. I should say mean, not average. And now I'm going to plug that into a calculator. Let's see what 46 divided by 18 is. It's about 2.55. Okay, so what does that tell us? It tells you two things. One, it's telling you that as far as we are concerned, the typical number of siblings is 2.55 siblings. Okay, what is weird about that? Yeah, so sometimes the mean is not that useful because it's literally impossible to have that many siblings, right? You either have 2 or you have 3. There's no, like, we keep the dead body of my brother and we count that as like 0.55 siblings or something like that, like, or my half sibling is only half of a sibling. It doesn't work that way. So sometimes, so we're going to talk about this eventually. In certain cases, for like discrete variables where you can only have discrete numerical variables where you can only have whole numbers, the mean is not a very good way to talk about what's typical because you might end up with a decimal. But does this make sense that if you wanted to, you could say 2.55 is the typical number of siblings? Like, that's valid, but there's also weird reasons why you might not want to say that. Okay, so the mean tells you that, what's typical. It also tells you something else really interesting, and it has to do with the graph. So we're going to go back up to this dot plot. So does everyone see the dot plot that I made here? Okay, so you can imagine, I'm going to erase these numbers on the bottom. Actually, no, I'm going to leave them there. 2.55 is like right... Wow, that did not want it to look like that. It is like right here. Does everyone see how I put the blue dot around 2 in the middle between 2 and 3? Okay, so imagine... I'm going to fill this in. Has anyone ever played on a seesaw at like a park? Okay, so let's say that you're an adult, and there's you, you're happy, and you're with your like little sibling who's much smaller than you. Is this gonna happen? Okay, what's usually gonna happen? Yeah, the heavier person weighs it down, right? So what's interesting about the mean is that you put the mean so that if each of these dots was like weight on the seesaw, the mean is where it would be balanced. So the mean is the point on the seesaw where the numbers would balance out. So I'm trying to do that. I can't type that anywhere. I'm just going to write it. The mean is the point where the numbers as weights would need to be balanced. So does that make sense when I say like the numbers as weights? Like if each of those dots weighed 1 pound and that's where you put them on the seesaw, the mean is where you would put the little place where it levers so that it would be perfectly balanced. I wrote that right here. The mean is the point where the numbers are balanced if you thought of this as like a seesaw. And that's actually why we like the mean, because it tells you where the balance point is, which is actually sort of useful sometimes. Okay, making sense so far? Anything we want to ask? Okay, so I'm going to scroll back down. Okay, what was horrible about calculating the mean? Like, would you want to do this yourself? Okay. Yeah, counting them, imagine if you had like 1,038 numbers. Can you imagine having to go and just count them Like, eventually you'd be like, I don't even want to do this anymore. Okay, now here's sort of a crazy thing. Like, how many people are there in America, approximately? Any guesses? How many Americans are there? 6 million is how many people are in the Bay Area. What? 360 million, approximately. Does anyone know how big a billion is in terms of millions? What is a billion? How many millions does it take to get a billion? Thank you. How many Chinese people are there? So that's like 1,300 million, and there's 360 million Americans to give you an idea of like how much bigger their country is. But anyways, imagine if you wanted to calculate the average age of Americans. You would have to count all 360 million of those numbers. Can you imagine trying to do that by hand? It would literally be impossible. When they used to actually when they first did the census before there were computers, it would take them 10 years to do all the calculations. That's why they only do it every 10 years. Does that make sense? Like in our Constitution, it says you have to do a census every 10 years and like find the average age and stuff like that. When there were like 10 million Americans and they had to do all that by hand, some poor, sad soul would have to go through the 10 million numbers and count them and add them all together. Like, it sucks. So anyways, we're going to talk about how do you have Wolfram to do this. So how will Wolfram help us? Well, guess what? It can calculate all this crap for you. Thank God. So we're going to discuss that now. Wolfram to the rescue. So I'm going to change my screen so we can look at Wolfram. Okay, does everyone see does it say datasets now? Okay, awesome, cool. So I'm going here because we're going to download, remember how we import the data from Wolfram? So I'm going to go to this thing that says age at Mar. So this is information about how old women were when they first got married for 5,534 women. So they interviewed 5,534 women and asked them, hey, when you first got married, how old were you? Okay. So I'm going to scroll down to where it says CSV, and I'm not going to download it. I'm going to copy link by right-clicking. Remember how some of us, we figured this out yesterday? There we go. Yeah. Okay, now I'm going to go over to Wolfram. I'm going to make a new notebook. And I'm going to say my data equals import, and I'm going to paste in that link. And then what do I have? Let me make the font a little bigger so you can see it. Zoom in, zoom in, zoom in. There, can everyone read that fairly nicely now? And I'll there we go, cool. Okay, so what else do I have to type after I put the link? What do I have to write now? Okay, that's next. It's there. So we'll put the header lines, yeah. Header lines. Arrow 1. There's also something else I have to put. There's one other thing. Yeah, you have to tell it that you're downloading data. Cool, now I go Shift Enter. Okay, so it's downloading all of that. And look, here's a bunch of ages. This woman was 32 when she first got married. This woman was 25. This woman was 24, 26, 32, 29, and so on. So does everyone see all those numbers? right? Okay, now you can start asking things like, hey, give me the dimensions of all of this. So give me the dimensions of my data. Okay, so I have information about 5,534 women, and I have one variable about them. Remember how we learned about the dimensions command? You always just want to verify. So let's go and let's type, we'll say, we have the one variable age at first marriage about 5,534 American women. Boom. Cool. You always just want to say that so you just remember later what you're dealing with. Okay, so the way you have it calculate the mean is pretty straightforward. So here's my data. I want all of the rows, and my variable is called age. Okay. So I'm telling it, hey, take my data about all of those people, and here are their ages, and what you do is you put / mean, and it will calculate it for you. Okay, and it gave you a fraction. If you want it to give you a number, you just do / n. So apparently, what was the typical age at which women got married? 23 and a half, about. Okay, so you have to, so there's two things to it here. The first part, which I'm highlighting, is you have to give it the data. So you give it the name of your data, you tell it to use all of the rows, and then you tell it the variable that you want to take the average of. I want it to take the average of age. Then you do // you tell it to find the mean for you, and then you do / that tells you to turn it into a decimal. So I'll leave that there. And then eventually next week we'll do like an assignment where you do this yourself. Okay, remember we're building up to this. You did an assignment where you imported the data. Now eventually you'll import the data, and then you'll have to have it calculate an average for you. Okay. So let's go back to the notes. There's some other stuff we need to talk about. Okay. So the dot plot, it's a nice graph. It's easy to look at, but there's a better graph that we're going to be dealing with. And it's called the histogram. So the histogram is a better version of the dot plot, basically. So I'm going to explain to you how this works. So the histogram is what we're primarily going to use to look at data. It's like a easier to read dot plot. Or it gives you more info. It may not be necessarily easier to read, but it's definitely more useful. Okay, so the dot plot, the way that it works, is that each number is a dot. So let me just I'm going to split this up. Let's do. Okay, so for the dot plot, each number is a dot. Okay, now the problem with this is that if you have a lot of dots, it gets a little hard to notice the patterns that are happening. So I'm going to put 2 dots. Oops, it's not letting me write. Something's going wrong. Sorry. Okay, there we go. Now I can put the dots. So I have 2 dots at 0, 3 dots at 1, 2 dots at 2, 4 dots at 3, 2 dots at 4, and 1 dot at 5. So looking at it this way, like there's a lot of up and down movement. So do you see how the top sort of goes like this? You see how like I drew that overlay there to sort of see what's happening with the number of them as I'm looking through it? Okay, so there's a lot to see here. The histogram does something really interesting. So for the histogram, instead of having a dot for each number, you put all of the numbers into what are called bins. So the histogram uses bins. And the way a bin works is that you're in a bin if you're between 2 numbers. So what I'm going to do is I'm going to make a histogram with 2 bins. Okay, so the first bin is going to go from 0 to 3. But what's going to happen is that 0 is included. Hey, did you do beef?
Yeah, I'm gonna do it.
Do it first before you go. Sorry, my daughter's like trying to escape. Do your thing first, or walk him.
And then I can go?
Yes. Okay, cool. Parenting achieved. So the way this works is that 0 is included in the bin, but 3 is not in the bin. So when I say that the bin goes from 0 to 3, the number on the left will put you in the bin, the number on the right will not put you in the bin. Okay, so how many dots do you see, or numbers, were there between 0, that were from 0 to 3, not including 3? Well, there were these 2 zeros, the 3 ones, and the 2 2s. So that's 1, 2, 3, 4, 5, 6, 7. So what you would do is you'd make a bin of height 7. So the height of this bin is 7 because there were 7 numbers between 0 and 3, not including 3. Now your next bin will go from 3 to 6. This one actually includes 3, because 3 is on the left now. So for this one, 3 is included in the bin. 6 is not in the bin. And then you need to count, well, how many numbers were there between 3 and 6? 6 not included. So let's use a different color. So you get 1, 2, 3, 4, 5, 6, 7 numbers. So this bin looks like that. They're both height 7. So you might be wondering, like, why do we care about this? It's because when you look at the dot plot, do you see how it looks like there's a lot of movement up and down in terms of, like, the numbers? You see how it goes up and then down, and it goes up and then it goes down again? So it looks like there's a lot of change. The histogram smooths that out. This actually is telling us, like, actually, as far as we're concerned, there were as many people between 0 and 3 as there were from 3 to 6. So it's just flat the whole way. It actually, we shouldn't think of it as like going up and down like what the dots showed us. Because there's a dot for every single number, you see a lot of fluctuation. The histogram smooths that out, and it actually is telling you, oh, it actually was pretty constant. Like, there wasn't a lot of change, all things considered. Like, if you look carefully at the one on the left, you see all that up and down. Okay? Sort of making sense? Okay, so last thing we're going to do is I'm going to show you how to have Wolfram make this for you, because like graphing it by hand is really annoying. Oh crap, that's not what I wanted. That's what I wanted. Okay, so the nice thing about Wolfram is that the command to do the histogram is going to be a lot like the command to do the mean. So you're going to tell it, hey, get my data, all the rows of variable age, and then I'm going to put a // and guess what's going to go after the //. We want it to do a histogram, so what do you think we're going to write after the command which tells it to look at the age? Yeah, uppercase H. And if you look, it shows up histogram. You do shift enter, and then there's your histogram. And you can see it. Do you see how it shows you the little bins? Okay, and now this is sort of the cool thing. What was the mean that we got? 23, right? You see how that's right above? If you look, that highest bin, look where it falls approximately on the x-axis. Do you see how it's super close to 23? So that's one of the reasons we usually like the mean. It's usually the value that occurs the most. That doesn't always happen, but usually. So it's a good thing to write that down. Usually, when you look at the histogram, the tallest bin will be the mean. And in fact, we're going to study, like, when does that happen? Because sometimes it doesn't. That's why I'm saying usually. Now, what's the youngest? If you look at these bins, some of them are sort of shocking. There were some rather young ages where these women got married. Like, there's a bin that's approximately what age? Yeah, and actually what's cool about Wolfram is that you can hover. Oh no, it won't let us hover over it. Yeah, there's a bin that's like right here and like right there. It's like 13 years old. So there were apparently people getting married at the age of 13. They're very small though compared to the whole thing, right? What's the oldest age at which women get married for the first time, approximately? Can make it a little bigger, easier to see. Yeah, like around 43 or so, something like that. It's sort of hard to say. But like, yeah, somewhere around 43. So the histogram gives you a good idea. Like, most common age at which women get married is 23. Sometimes as young as 13. Sometimes as old as 43, and a lot of stuff in the middle. So this is with this distribution view. You're looking at everything is the whole idea. Okay. So far today, I told you how to find the center, what's typical. 23 was a typical age at which to get married. And then now we have a good idea of like what the shape looks like. That's what we're going to talk about next time. Okay, so we're just going to end here. Does that make sense? We'll pick up on Monday. So before you go, please write, I was here.